Welcome back. So today we're going to be discussing tangents. Okay, so these are tangents to a circle. We've been talking about circles, we talked about central angles and inscribed angles. Now we're going to be talking about lines that go outside of the circle. So our first one is tangent. So tangent to a circle is a line in a plane of a circle that intersects the circle in exactly one point. Okay, that point of intersection is called the point of tangency. Alright, so if we have a line that comes near a circle and it touches that circle at exactly one point, then we call that tangent, and that point is our point of tangency. So then we have a couple theorems. Our first one, 10.9, says if a line is tangent to a circle, then it is perpendicular to the radius drawn to that point of tangency. So if we look down here at our picture, we have a line that is tangent to our circle. So that means that this line is perpendicular to this radius that we have drawn. So if RT is tangent, then we know that OR, which is our radius, is perpendicular to RT. Okay, that's going to be very helpful because we know a lot of things about right triangles. So that's going to make a right angle in there for us. So let's move on. We have a couple more theorems. So we have 10.10. It says if a line is perpendicular to a radius of a circle at its endpoint on the circle, then that line is tangent to the circle. So all that's saying is up here with this last one, it's just doing the inverse. If we know that these two lines are perpendicular, then we know that this line is a tangent line. Okay? Alright, and then 10.11. Sorry, let me scoot down just a little bit more so you can see all of that picture. So 10.11 says if a segment from the same exterior point are tangent to a circle, then they are congruent. So we have two segments here. I'll call this one A. Two segments that start with the same exterior point, and they are tangent to my circle. So we know that these two segments are congruent to each other. Alright, so now that we have that information, let's go on and work some examples. Okay, so we're going to start with number 1 here. So we have a picture, and it says ED is tangent to circle F at point E. Okay, so if this line is tangent to this, then we can say that this is a right angle. So we have a right triangle, and we're trying to find X. Alright, so we have two legs of our right triangle, so you can use Pythagorean Theorem, or you can look for one of those Pythagorean triples. So Pythagorean Theorem tells us we're going to take our legs squared, so 3 squared plus 4 squared equals our hypotenuse squared, which is x, so x squared. 3 squared is 9, 4 squared is 16. 16 and 9, we get 25 equals x squared, so then x equals 5. Okay? And that is that whole length of that side. Alright, let's go on and look at another one. So for this one, it says determine whether MN is tangent to, sorry, I forgot to finish that. So if MN is tangent to circle L. Okay, we want to know if MN is tangent to this circle L. So how do we do that? Same way as we did before. We're going to be looking to see if this is a right triangle. If this is a right triangle, so we're proving using Pythagorean. If it is, then this is indeed tangent. Alright, so if we look at this picture, you'll notice that ON is 2, but they didn't tell us LO. Well, we know LO because that is a radii, and so is LM. So if LM is 3, LO must also be 3. Okay, so again with our Pythagorean, we have the legs, so 3 squared plus my other leg is 4 squared equals 3 plus 2 squared. That's my hypotenuse. Okay, so we have 9 squared plus 16, or excuse me, 9 plus 16 equals 5 squared. So 25 equals 25. So did this work? Yes. This is a right triangle. So we know that MN is perpendicular to LM. Okay, MN is perpendicular to LM because this is a right triangle. So MN is tangent. All right. Okay, let's keep moving. Excuse me. We have another example down here. So this time we're going to determine whether PQ is tangent to circle R. Okay, so we're looking at our pieces again. Again, you'll notice they gave you this leg, QR, they gave you the other leg, which is QP. They only gave you part of the hypotenuse. They gave you SP, which is 4. We know SR also has to be 4 because our radius, QR, is 4. So we can go ahead and add that piece in. So then Pythagorean, we're taking our two legs, 4 squared plus 5 squared equals 4 plus 4 squared. Okay, 4 squared, we've got 16, 5 squared is 25, 4 plus 4, we have 8 squared, 25 and 16, we've got 41, and 8 and 8 is 64. Okay, so are those equal to each other? So no, so this is not a right triangle. So then we know that QR is not perpendicular with QP. So then we can say PQ is not tangent. Okay. Alright, questions on those? Please make sure that you post those in your WSQ form, or you can ask them in class tomorrow. Alright, let's keep moving. We have another picture here. So this time we're dealing with our two different pieces from an exterior point that are tangent. So if you remember, that theorem said that those are congruent to each other. So we're finding x here. We're going to assume that the segments that appear to be tangent to a circle are tangent. Okay, so let's go ahead and look back at 10:11. And it said if two segments from the same exterior point are tangent to a circle, then they are congruent. Okay, so that means if we look at this picture, AB and AC are congruent. So AB is congruent to AC. That also means for this one over here, AC is congruent to AD. Now if you remember back when we were doing proofs, we had one of our different properties that said if AC is congruent, AB is congruent to AC and AC is congruent to AD, then we know AB is congruent to AD. So AB is congruent to AD. The reason why this is important is because we have two expressions, one's for AB and one's for AD. Now that we know that those are congruent, we can set them equal to each other and solve for x. So we have a negative 2x minus 37 is AB equals AD, which is 6x plus 5. Okay, now we're going to be solving. So I'm going to move my x's together. So I'm going to add 2x to both sides. So I have negative 37 equals 8x plus 5. So I'm going to subtract 5. So I get 8x equals 42. And that is a negative. So then we're going to divide by 8. we get x equals, and I'm actually getting a fraction here. So 40 would be 5 1/4, and negative 5 1/4. So we're going to plug those in and see if those work or if we've made a mistake somewhere. Okay? Alright, so we've got a negative 2x minus 37, negative 2 times a negative 5 1/4 minus 37, so that would be 10.5 minus 37, so that would be 26.5. Okay, so then we're going to work on the other side. So then when we're working on the other side, we have 6x plus 5, so that's 6 times a negative 5 1/4 plus 5. 6 times 5 would be 30, and then we've got 6/4, so we've got 31.5 plus 5. So we have a negative 26.5. They did come out to be the same number, but they're opposite signs. So we're going to go back to the original problem and look and try to find our error. Okay, so if we come over here, we have a negative 2x. Oh, I wrote minus 37. That should be plus 37, so that's where our error is. So then when we come down here, we're subtracting the 5, but this should be a plus 37. So that actually gives us 32, and that's a positive 32. So I'm going to put 32 in here. So 32 divided by 8 would give us 4 equals our x. Okay, so now again we're going to come over and we're going to check our work and see if this works this time. Okay, so again we have a negative 2 times 4 minus 37, or excuse me, that should be plus 37. So a negative 2 times 4, it's a negative 8 plus 37. So then we end up with 29. So then on the other side, we had 6 times 4 plus 5. 6 times 4 is 24 plus 5 gives us 29. This time we have them being equal to each other, so we know we have the correct x value. So x equals 4. So go back up to the original problem. It says find x. Assume that the segments that appear to be tangent to the circle are tangent. So we did find x, and that's all it asked for. So we are finished with the problem. X equals 4. Okay? Alright, that is all for today, and I'll see you in class tomorrow.